introduction, and thank you for being here today. And yeah, my name is Teemu Kinnunen. I'm a data scientist from Futurize. Futurize is an IT company from Finland. We have around 600 people, 8 offices in Europe. And I'm super happy to be here today to talk about my favorite topics: computer vision, deep learning, and of course self-driving cars. And yeah, so actually when I told to my daughter that I come to Vienna to talk about self-driving cars, she asked that why can't you talk about horses and stars? Think about topic end-to-end deep learning systems for stars and horses. That would be cool. Okay, but that's not my title today. Today I will talk about end-to-end deep learning pipeline for self-driving cars. And if you're wondering, the image that I have on my slides, it's our car what we built in Munich to have a toy car that we can train to drive around the track. And actually, it started as a hobby project. It became a bit more serious. It was working? Okay. Maybe now. So, we started a hobby project to build this self-driving toy car with my colleagues in Munich and on the other sites in Finland and in other offices. And we decided that, hey, let's have a competition between the offices. And every year, Futurize, we as a company, we have a summer party. So this year we had a summer party in Tampere. And we decided that, hey, let's have a race in Tampere. So let's have a race between different offices to compete together to see that who makes the best car. And we actually invited also some of our clients. And this was like really good tool to learn about deep learning, how to build pipelines for deep learning and that kind of things. How many of you have been playing with deep learning, trying to classify MNIST images or CIFAR images or something like that in Jupyter notebooks or somewhere? I see some hands. Cool. What about how many of you have actually deployed something into production, deep learning stuff? Still some hands. What about embedded devices? Not so many hands anymore. Okay, in this talk, I want to share my journey from like having something quickly hacked together in Jupyter notebook kind of environment, and then what it takes to actually put that into production, to run it for real. Now it works. Cool. So I start with some introduction, giving some background on this thing, and then we go through different steps of pipeline to build this deep learning system. So we start with data collection, then we talk about data processing, then machine learning modeling stuff, and then how we evaluate and analyze those models, and then how we actually deploy those models on the cars that we can actually drive them around the track. And then in the end, some conclusions that what did I learn from this journey. So let's get started. So goals for the pipeline that I thought that should be done is that, okay, first of all, it should be fully automated. So whenever somebody is driving the car around the track, we should collect some data about the driving, and then we should train new models, and then deploy those models automatically. So basically what should happen is that when somebody is driving the car around the track, the car should learn to drive better next time. This is what I would like to have. We are not quite there yet, but we are moving in that direction. In addition, it should be collaborative. It should support people working together. So when you have more than one data scientist working in the project, it would be nice if they could work together, build different kind of models, and compare that which of the models works the best. And they should share code and results and data together. It should support that kind of things. And then the last, it should be also like support that you can actually reproduce those results that you did last time, or reproduce those experiments that you conducted last time. So when you have these quick hacks, as we did in the first place, it's quite easy to lose track that which changes actually improve the results. And you don't know if you even get better results now than like 1 week ago. So you should have some method how you can actually reproduce those experiments that you did with new data. And when you make some changes in the code, you should see that what kind of changes you had and how did it affect your performance. So you could gain better understanding that what kind of changes impact in the performance. So those are the goals for the pipeline. In this experiment, we used DonkeyCar platform. So DonkeyCar is an open source, do-it-yourself, self-driving platform for small-scale cars, meaning that you can buy an RC car from a shop, and then you can plug a computer like Raspberry Pi or NVIDIA, such a Nano or something like that, and a camera, and then you can train your own models to drive the car. It's an easy way to get started with self-driving cars. It provides you controls to control the car and capture images from the camera. So you don't need to know much about electronics. So you just need to plug in the cables, basically, and then you just install this DonkeyCar software on your mobile computer, and then you can start collecting data and training models. It provides you a baseline AI, so some simple neural network that you can get started with, and a method how you can train those models on that network. Of course, it doesn't support you that you could train models on cloud, so you need to train those models on this Raspberry Pi. So if you want to do something in cloud, you need to do some tricks there. And there is a DonkeyCar simulator that you can use, so you don't need to even build a car. You can start with the DonkeyCar simulator to get some data, train models, and see that how your network works in simulation. Cool. So let's get started with the model that we built for the competition. This is not how you should do it. This is just what we did, and this is the thing that I wanted to change into more robust thing. So we had a car. Then we uploaded data to Google Drive from the car after driving the car around the track. Then we had a bunch of Google Colab notebooks. So these are notebooks running in Google Colab, Google Cloud. And so we had Colab notebooks to clean the data, process the data, and then train models. We stored those models in Google Drive, and when we wanted to deploy those models, we downloaded those models to our computer, and then we just copied them to this car running Raspberry Pi. And of course, there is lots of manual steps here, and if there is someone who doesn't know anything about the project, it takes quite much time to understand that how they can contribute to the project. And this is not what you want to have. And of course, if you collect new data, it takes some time to deploy a new model, and this is not what you want to have. And that's why we wanted to change it. So this is like the target thing that what we want to have. So we want to have a data collection thing where we can collect data, so when we are driving the car around the track, like human being driving, we can collect new data. And then we have data processing pipeline, cleaning the data from human errors and other errors, and then transforming that data format into format that you can feed the machine efficiently. And then we do some machine learning modeling, teaching the computer to drive the car. And then finally, when we have trained a model, we evaluate it and try to understand that what kind of mistakes it can make. And then we deploy the model on the car. So this is the pipeline. And I will go through these steps now. So let's get started with the data collection. So goals for the data. So the quality of the data should be really high, so it shouldn't contain any mistakes or some other errors in the data. And in addition, there should be enough variation in terms of illumination changes and like those driving paths should be a bit different every time human is driving the car around the track. And in addition, it would be nice to have also some different sensor configurations. So in addition to camera, you can have LiDAR and sonar and that kind of sensors attached to the car. So it would be nice to collect also different kind of sensor data. So you can evaluate that which of the sensors can provide useful information for you. And goals for the data collection pipeline, it should be automated. So whenever somebody is driving the car around the track, it should collect that data automatically and then upload that data to cloud, so it could be available. It would be available for the data scientist or whoever to build new models on top of that one. And then you should also collect some metadata about the driving session, like who is driving, the day, and so on. So when you analyze those results after you have trained a model, it helps you to understand that maybe there is just a bad driver, for example, and creating bad data so you can maybe drop that data away. Cool, getting data. So first you need to have a car. So we ordered a car. We got bunch of pieces for car. We spent few hours to build a car, and then we plugged a computer on it, added some tape, and finally we got our first prototype for the car. And then we made also a track to collect some data. This is not very typical data science project, how you start to collect data, but it was really interesting and fun. And then here is one example how the data looks like. All right. So the white arrow is human driver, and then red arrow is AI. And then we can compare that how well the AI is driving the car, and also how well the human is driving the car. It also makes some mistakes and some corrections, and then the AI would still drive straight. So it's quite interesting. And then you can detect that, okay, in which kind of cases it makes mistakes, and if it's always the same position or in the same place in the lab, that when it makes a mistake. Like here, the driver is making some some corrections, and yeah. Now we see that like the driver and AI didn't agree fully. And then you can apply like this Keras visualization to get heat maps that which locations on the image actually are important to make the decision also. So this is our data input. So our data collection pipeline. So we collect some metadata, then we drive the car. So we have a script that runs these things. So we collect some metadata, then it starts this DonkeyCar program in human driving mode, and then when it's finished, it uploads the data to cloud. First it zips all those collected data into one file, and then it uploads the files into Amazon S3. And then this is how the data looks like. So for each data point, we have a JSON file that tells that which camera image is referring to that exact record, and then we have timestamp, and then we have user controls. We have throttle and angle, and then it also tells that who is controlling the car. Is it user or AI controlling the car? All right, now we have collected some data. Somebody has been driving the car and collected some data, and we have it available in the cloud. So let's do some data processing. On high level, our data processing pipeline looks like this. So we have this input, is the raw input, what we have, and then first step we clean the data, and then we store that in a new place. After that one, we split the data in train, validation, and test splits, and then we convert those individual files into Tensorflow records that we can feed the machine efficiently to train those models. We tried different kind of approaches to clean the data. We tried to use some heuristics and that kind of things, but there was always some corner cases that we couldn't just figure out how to solve it. So this was our the best effort to clean the data. It's not very bad for if you drive the car for 10 minutes, it takes maybe 2 minutes to clean the data. So in the first step in this data annotation process is that we generate a video from those frames, and then some human being is watching the video, usually it's me, and then I just mark that which of the segments are bad and which of the segments in this video are good. And then I can use that information to throw away all the bad bits from the video or from the recorded data. And then I store this good data in clean input directory in S3. Then one very important thing is to split the data in a good way. So we split the data in 3 different parts. So for the training part, we used 70% of the data, and the training part is being used to train those models, those neural networks, so optimizing those model parameters. Then we use validation data, 15% in our case, to monitor that how well the learning is going. And if we notice that, okay, like after each epoch, we use validation data to see that if the loss is going up or down, and if we notice that loss is going up, so it doesn't improve anymore, we can actually stop the training to avoid overfitting. And it can be also used to optimize some hyperparameters like optimizer and learning rate and that kind of things. And then when we are happy with the model, so we can train different models, and when we are happy with them, we can actually use test data to test that which of the networks works the best. And this is really important that you don't use this test data too often. So like every time you train a model, you use test data. You shouldn't do that, because then you start to leak data, information from test set into your validation and training, and that's not a good thing. So you should use test data only when you are happy with the model and you want to see that how well it actually performs. And in addition to that one, so since we have temporal data, it's also important to divide this data based on time. So in our case, we used 70% of the data to train the model. So first 7 bits in this case to train the model, and then 8 bits into validate, and then the last part to actually test the model. And usually we had many driving sessions, so we were collecting data in many days and on many different days, and so on many times a day. So we had different driving sessions, maybe we had different drivers and so on. So we split each driving session separately. So and the motivation or idea here was that we wanted to like see that which of the driving sessions is the most difficult, and to be able to, and it can be difficult to generalize. For example, if you change the track, so driving session 1 and 2 are done on one track, and then you go to different track on driving session 3, and it's not really useful to try to see that if it can generalize to different tracks in our case, because we didn't have that much data. So that's why we split each driving session in train, test, and validation. Cool. And then since when you are recording data with DonkeyCar, you get tons of JSONs and images, and this is not the most efficient format to train models. So you need to convert JSONs and images into something more efficient, and one of the approaches or things could be this TensorFlow records. And this is like a binary format, similar to protocol buffer, that can be used to store information and easily used to train those models. So basically what we had a bunch of records, and then we had a bunch of images, and then we had a script that converts these JSONs and images into TensorFlow records. And here is a code example how it works. So first we load all the JSONs. So we give a directory where all the JSONs are. So we load all the JSON files into list of dictionaries. So records is equal to load tub data to records line. And then we open a writer to write these TensorFlow records, and then we just loop through the records, and then we serialize each record. So first we read the image in the string, and then we take the angle. When the user has been driving the car, we take the angle and then the throttle, and then we serialized that one into example. And here is the serialization part. So like I said, that it's a dictionary. So there is this feature dictionary that is being used, and you need to serialize each of the value in here. And this is from the TensorFlow script that you can check that what does it mean to convert these like strings into bytes and so on. But yeah, basically you need to serialize each of the argument here, and then use this TensorFlow train example to convert that feature into serialized mode. And then you just write the example into this TensorFlow records. Cool, and that's how you convert your data in more efficient format. All right, now we have collected data, then we have cleaned the data and converted that data into format that we can actually use to train models. So now it's time to talk about machine learning modeling and making the magic happen. So what essentially happens is that we are transforming pixels into actions. So pixels are the images coming from the camera, and then actions that we want to make are the angle and throttle. So we want to steer the car and control the speed of the car. And then, of course, we use AI to solve this problem. It's easy. What I mean by AI, we usually have, like in case of computer vision, we use convolutional neural networks. And what does it mean? That we have, in convolutional neural network, we have convolutional layers, and then we have some dense layers, in our case, since we are doing regression. So in convolutional layers, we have convolutional filters, activation functions, and pooling layers. And then on dense layers, we have flattened layer, and then we have a bunch of dense layers after that one. And convolutional neural layers are being used to extract features from the images. So it can extract edges and corners and other kind of shapes that are relevant for the task. And then we use dense layers to make the final decisions. So based on the extracted features, it tries to predict that in which direction the car should go and how fast. And the magic in deep learning and convolutional neural networks is that it actually learns to extract features from the images that are relevant for the given task. So let's go a bit deeper. So what does it mean? And again, let's go to code. So our input for this network is an image, so the second line here. And then we have a bunch of convolutional layers here. And then we have those decision layers, dense layers, that we use to make those predictions. And then on the last line, we have input, which is the image coming in, and then we have outputs, which are the angle, the steering angle, and then throttle, the speed of the car. And let's go through this one by one. So let's start with the convolution. What does it mean? So we have an input image, and then we have a filter. And then this filter goes through the image, and then we get some responses. So in this case, this filter is detecting horizontal edges from the image. And since it's a convolutional network, we can have a bunch of these different kind of filters. So if we rotate that filter 90 degrees, we start to get vertical edges from the image. And these filters are manually made by me, but in practice, when you train neural networks, it actually learns the parameters of these filters. So it learns those numbers that what it should put there in order to extract features that are good for the task. And instead of having just 2, it has a bunch of those filters. So it has, I think in that example, there was 24 layers or filters on the first layer. And then it can combine many of these layers together. Okay, let's move into max pooling. So what does it mean? So we have this feature map, this gray image from the previous image, but now it's just 4x4. And then we do 2x2 max pooling for the image. So meaning that we take 2 columns, 2 rows of blobs, like this red area, and then we take max value out of that one, and then we store that as an output for the next layer. And then we do the same for yellow region and green and blue regions. So we take max of these regions. And instead of max, you can also take average, and you can compute average over that region. So you get different values. And the intuition here is that sometimes we are not so dependent on that in which specific region something happens. We are just interested that if there is a corner or some specific shape in the picture, and we just want to know that how much there is this kind of feature in the image, and so on. So we can use this one, so we can get some spatial invariance in the model. And of course, we can also reduce the number of parameters in the model when we use max pooling. All right, that's about convolutional layers. So let's go into dense layers. So the first layer was flatten, which means that it just takes this matrix and then it converts that one, concatenates all the rows together to make a long vector. And then the next layer, it's necessary to do that because then the next layer is dense. So we want to, for the dense layer, we need to have vector inputs. And I believe that many of you have seen MLP networks many times again, so I'll just go through this very quickly. And the idea here is that you define, or based on how many inputs do you happen to have. In the previous example, we had vector of 16 elements, so we would have 16 inputs. And then based on how many outputs do you have. If we just want to control the steering of the car, we have only one output. If you want to control also the speed, then we have two outputs. But in this case, we have only one. And then what happens here is that, and then we have some hidden layers in between input and output. And then user or data scientist is defining that how many neurons they want to have here. So in this case, we have only one. So what happens here, it just computes weighted sum of these inputs. So for each input, there is a weight, which is learned during the training phase. It computes weighted sum of those inputs, and then it applies some activation function. It can be linear, meaning that it doesn't do anything. It can be done a sigmoid ReLU or something else. And then it outputs that value for the next layer. And the last element here is dropout layer. So the dropout layer is used to regularize models. So when you have dense layers, they become quite complex, meaning that they have lots of parameters quite quickly. In this example, we have 5 inputs, and then we have 1 output, and then we have 2 hidden layers with 5 neurons on each layer. And each arrow is one connection. And we can see that there is already quite a few arrows, which means, and each arrow is actually a weight. So we can see that there is already quite a few weights and parameters in the model already, even though it's really simple model. In practice, we have much more neurons and more complicated models. So it's quite easy to start to overfit. And by overfit, I mean that it starts to learn some specific cases. So there is one input, and then it learns what is the right output for one specific input. And this is something that we want to avoid. And one way to avoid that one is to use dropout. And by dropout means that you temporarily just disable some of the neurons in your network. And what happens is that those neurons that are not deactivated needs to take the responsibility of those that are disabled. And this helps to generalize those models. And this is, for example, in each batch, you select which of the neurons you disable during the training phase. Of course, when you run predictions, all the neurons are being enabled. Cool. Then let's talk about code and how to actually train those models. Now we know what kind of pieces do we have in this convolution neural network, so how to put everything together and train models. So now we have our codes. We had this Google Colab notebook. Now we have codes in GitHub, which is nice. Then we have a training script that can be run by anyone, basically. And then we have a user who can control different parameters, how to train models, which kind of architectures they want to use, and so on. And then we have our clean, nice data sets sitting in S3 that can be fed into this training algorithm. And then we have been using High machine learning pipeline to actually execute these trainings. And in High, you can define that what kind of experiments you want to run, and then it keeps track of the outputs. So it stores those models back to S3, and then it also keeps record of your results. So it monitors your training, and it keeps track of those results that you gain. And here is an example of how our training script looks like. I omitted some of the lines because it's a bit long, maybe it needs some 1 or 2 iterations to make it pretty. So first we read some training data sets, so this Tensorflow records, and then validation records. And then we define what kind of model we want to use. And then we actually just fit the model pretty much as you do when you do some basic experiments with Keras in Jupyter Notebook. So this is pretty much the same, except that instead of keeping your images in your memory, it actually uses this TensorFlow record set that it fetches the data when the model actually needs it, or when the training actually needs it. So that's nice. Cool. Now we have trained our model. So let's evaluate it. So the standard way is to use some metrics that you can use to evaluate how well the model is working. And basically it gives you that how similarly the computer is driving the car compared to AI. And then like the next step, of course, it doesn't help you. You just get some number out that, okay, this is the root mean squared error for this model, but it doesn't explain that is it good or bad. So you need to see also that how well it actually works. And in order to do that, so you need to have the machine learning model that you just trained and data. And then you can measure like root mean squared error, for example, or mean squared error to see that how well it works. And then you can use this to compare different models or approaches that you have to select the best one. But if you want to reason that does it actually work and what kind of mistakes it makes, then you need to have some other tools for that one. So you want to know that when it fails, and then also that why it fails. That's the next step here. And we built this kind of tool. I really hope that this video works. Well, I just explain. So now we have white arrow shows that in which direction the human is driving, and then red arrow shows the direction where the computer is driving the car. God damn, it was working when I tested just before this presentation. I will show you after the talk if you are interested. And then you can see that like in the situation that what kind of typical mistakes the AI is making, and sometimes even the human is making mistakes, some like that it's going off the track and so on. So this is really nice tool for that. And then let's talk about deployment. So now you have your model that you are happy with in S3, and then you optimize your model. You can convert it to Tensorflow Lite to run it faster, and then you deploy your model, and then you hit run, and then your car explodes. And of course, this is not what you want to do. You don't want to be repairing your car like every week. You want to do something more intelligent here. This is what we did for the first time. But we did learn that, okay, this is not how you should go. So we have different levels of how we actually deploy these things. So like level 0 is just that human is driving the car, and we are just collecting predictions from the AI, and then we can compare those predictions with the human driver to see that if they agree or if the AI is making good decisions. Then level 1, AI is controlling the steering of the car. Human is still controlling the speed of the car, so we can still avoid all the big accidents from happening. So we can drive really, really slowly to make sure that the AI doesn't break our car. And then on level 2, we can let the AI control steering and speed of the car, and then we can still have some kill switch to stop the car and start the car and that kind of things. And this is how we deployed. And then, summary, final thoughts, what did I learn during this project? First of all, the quality of the data is super important. So when we were training our first models, we were wondering that why the error is so big, why it doesn't learn anything, and then we realized that our data was just not very good. So we had driving errors, we had some data from being collected when the car didn't move at all and that kind of thing. So it did learn that it shouldn't do anything or something like that, something really stupid. So you need to clean the data before you start training any models. And then the second thing that we did learn is that it's a really good idea to keep track of the model complexity and benchmark the model, like the performance of the model, how quickly it can make inference, how quickly it can make predictions that in which direction it should run. So we had really good model running into the Colab notebooks that was making really good predictions, but when we deployed the model, our car just went straight, and we were wondering that what's going on. And then we realized that it's just so slow that it can't turn before it's too late already. And then this is like that applies to all the software projects. So do not hack the code on the car, do not hack the system that is in production. You should hack your things on your own computer, then use Git, and then just pull the changes from repository. This helps you to track that, okay, what kind of changes you made and what you should do if you want to go back or forward or something like that. So that was really interesting learning also. That was something that applies to everything. And then when we were developing these models in Google Colab, we didn't have a system where we track our results. So we were just making some changes. Sometimes we changed the data. Sometimes we made some changes in the model. Sometimes we changed some processing or parameters or something like that. And we didn't track that, what kind of changes we made, what kind of results we got. We just moved forward. And then we didn't know that if we are improving or not. And that's not how you should do if you are doing it for money. And last but not least, do not break the car. Use safety procedures to keep the car in one piece. So as you can see from our car, it got quite a few hits. We had to add even more tape to that car in different places to keep the car in one piece. And this applies to all the like machine learning projects when you deploy some new things. So first you can just run the model in like host mode, that you just record predictions and then you compare, or you can analyze those, what kind of predictions the model is doing, and then you can reason that does it make sense. And then you can add or roll out the model when you feel confident that it's doing good predictions, for example, for some of the users, and then to everybody when you feel good about it. Cool. Thank you.
Thank you, Teemu. And we have really a lot of questions this time, okay? And luckily we've got quite some minutes to go through these. So let's start off with the first one, yeah?
Yeah.
So this one says, is Tesla far ahead of the competition in regards to full L5 autonomy, especially regarding the data of 500,000 plus cars in the real world gathering real world data?
Yeah, I think the data is really important when you are developing these cars. This is what we did learn even with our toy car, that it's really the crucial thing. And I think that they are like one of the most bravest, and they are pushing the innovation forward. I don't know, it would be really interesting to discuss with Elon Musk and maybe Andrei Karpathy and get their opinions about that, how far away they are. I think so that Elon is somewhere here, Karpathy is somewhere here, about like how far away they are with this level 5 autonomy. So yeah, but yeah, data is really important. I think that it's like already they can drive somewhere in California when there is no snow and everything is good. They can drive already better than human beings. But when there is something surprising happening, then of course surprising things happens, and that's not very the thing that what you want to have in self-driving cars.
Thank you. Maybe we can get Elon next year to discuss that with us. So the next one says, for someone with no experience in self-driving cars, how long do you think it takes to build a toy project?
That's a good question. I was wondering the same last summer. So with this DonkeyCar, I think that you can like get started with this simulator in one day. That's like really nice. But then if you want to build your own like physical car, it takes some time to assemble the car, plug the computer in it, and so on. But it takes maybe 1 weekend or something like that to have everything together. So it's quite easy to actually get started with this DonkeyCar platform. But it really depends if you want to build everything from scratch, like all the electronics and all the software running those electronics and discussing and that kind of things, then it might take a few more weeks.
All right, thank you. And when, in your opinion, will level 5 full autonomous self-driving cars be present in European streets? And will it be before 2030?
Yeah. I think that would be rich if I know this. So this is quite difficult question. I think it's like in typical cases, like common cases that we have enough data collected, I think that self-driving cars are already quite trustful. But there is still, like in Europe especially, there is like we have snow and we have different kind of weather conditions and surprising events happening. So like this level 5 it's not so easy to reach. So I think that there will be still, like in long future, there will be some cases where you need to have a human being driving the car. But I would guess that it's like rolling step by step. Like I already had this like in my presentation, like level 0, level 2, and level 1. And maybe it happens also in the same way that AI is driving the car when it feels that it's safe to drive the car, and then it can let the human driver take the wheel when it feels uncertain that what should it do.
All right. Okay, so let's look at this one. Your validation and test data come from the same sessions as training sets?
Yep.
Train sets?
Yep.
Shouldn't they be completely independent, to be fair?
Okay, I guess that it's well, we wanted to collect, like this question is regarding the driving sessions, so we collected data from many driving sessions, and we decided that it's good way to split every driving session separately, because sometimes we tested our car. This is based on the experience. So our experiment was, for example, that we collected first 2 driving sessions that we were driving the car around the track on clockwise, and then we tested that, hey, is it able to drive the car counterclockwise? And it wasn't. So we thought, okay, we need to split the data in the way that we can actually collect data from different cases, that it's okay for the car to learn to drive the car or control the car in both ways and in different kind of situations. So that's why we split each driving session separately into train, test, and validation.
Thank you. Okay. And someone asks here, is there a reason why you chose Tensorflow as an ML model? And are there any other ML methods that could be used for autonomous driving?
I believe that there is. So Tensorflow was selected because I had some experience with that one already before the project. And then it's being supported by DonkeyCar. And then also that it's quite nowadays it's also quite easy to compress the model into smaller size, that you can run more complicated models in real time or more efficiently on Raspberry Pi and NVIDIA Jetson Nano. And I don't know, for example, about PyTorch, that how small package you can make out of that one, and is it possible to run it on embedded devices? I don't know, but I believe that there are some other tools. But we already heard yesterday about ML core and that kind of things, but we didn't. I don't know if it's possible to run on Raspberry Pi. I think it just runs on Apple devices. So that was our choice of tool. Experience and then proven results.
Okay, very good. And okay, how long and how many people did you work with? So how long did it take and how many people did you work with on this project?
Yeah, I think so, like we had maybe 10 people in total, but this was a hobby project. So if we counted how many working hours or working weeks did we spend, it was not that many. It was mostly like that we had our client projects, and then in the evening we had some fun with the self-driving car. That was for the competition. And then afterwards I have been spending some time on the data pipeline, because it would be nice. It's nice to have something that everybody can run quite easily and get started and contribute. So like we had maybe 1 to 3 active people during the project in Munich to help with the car.
All right, cool. So I think we've got time for one more. Let's go for this. Did you train in simulated environments?
Yes, so I started before we got the car, because it took some time to actually assemble the car and get everything together. So I did some experiments with this DonkeyCar simulation thing, and that was the way how I got started. And yes, so I did train some models there and then tested them how well it works, and then already had some like architectures for networks already in place and data pipelines and that kind of things.
Okay, thank you. So let's give another warm round of applause to Teemu. Thank you.
Thank you.